Hello friends, so today we'll solve a numerical on balancing of rotating masses. So let us see the question first. A shaft carries four masses. There are four masses A, B, C, D of magnitude 200 kg, 300 kg, 400 kg, 200 kg respectively. Okay. Now they are revolving at the radii 80 mm, 70 mm, 60, 80. Everything is given in different planes. The planes are given with respect to A. From A it is 300, 400, 700, and the angle between the cranks are given anti-clockwise. Okay, from angle between A and B is 45, B to C 70, C to D 120. The balancing masses are to be placed in planes X and Y. So there are two balancing masses X and Y in different planes X and Y. Okay, so the distance between the planes A and X, so A and X, distance between A and X will be 100 mm, and between X and Y is 400 mm, and distance between Y and D is 200 mm. If the balancing masses revolve at a radii of 100 mm, so the radii for X and Y will be 100 mm. So find the magnitude and angular positions. So we have to find the angular positions and magnitudes of. So first of all, let us draw the position of the planes. Okay, so let's suppose this is mass A. Okay, now B is 300 from A according to question, like C and D. Okay, now let us write its distances. It is 300, it is what 400, okay, and it is 700. Now X is 100 mm from A, so 100 mm from A, so this is over here. X, A, B, C, D, and Y is at 200 mm from D. Okay, so it would be somewhere over here. Y 200. Okay, now let us draw a table for further details. So first of all, there will be a plane, mass, radius, centrifugal force upon omega square. So say directly say it mr. Distance from plane, so distance from plane say L, and now at the end couple. Okay, that will be mr into L. So we have six plane. Okay, we have six plane A, X, B, C, Y and D. So write it down. A, X, B, C, Y and D. Okay, now over here we could take any one of them as reference, but we'll take X as reference because it is at the starting, and if we'll take X as reference, then there would be only one unknown will be left, that would be Y. So let us take it is a reference plane. Okay, now we have masses given, say it is 200, say it is mx, B it is 300, 400, my and md it would be 200. Okay, now distance, what is the radius, it is given over here. Okay, so write it down, 0.08 in meters, 0.1, 0.07, 0.06, 0. It is 0.1. Okay, 0.1, 100 mm and 0.08. Now what would be the product of them? We have to do calculate it down. Okay, so I'll calculate in few minutes. Okay, and I'll resume later. So I have written down them, all of them. Okay, now distance, it would be, we know that if you have seen my older video, then you know that it is negative in the left side. Okay, and here it will be positive distance in the right side, okay, in the right hand side. So minus 0.1, it would be a reference, so it would be 0, and it would be 0.2, now 0.3, 0.4, and it will be 0.6. You could see in the diagram, okay, in the position diagram, okay, position of planes, in this diagram you can see this. Now couple the product of mr into l, okay. So I resume after a few seconds. Okay, here I have done all the calculations. So here we could draw, or we could draw two diagrams, okay, of force polygon or say couple polygon. But here we can see that in couple polygon there is only one unknown vector, that is my, and here there are two unknowns, mx and my. So it would be easier to draw this one couple polygon first, so that we could find my, and later we use my in this equation, in this force polygon or say centrifugal force diagram. By using that we could find mx as well, okay. So first of all let us draw the vector diagram for couple, okay. So draw couple polygon. At first we will draw couple polygon. Couple polygon, okay. Now let us draw. So let us draw the couple polygon, okay. So for that we will see from the table, okay. Take data from the table. Now minus 1.6, okay. First of all negative 1.6, you can we can take any scale as per your ease, okay. So I'll take 1.6 exactly. Okay, say it is O dash and this is A dash. Now in A to B, okay, A dash to B dash. 45 degrees. So draw A to B at 45 degrees. 45 degrees, okay. Completing this diagram I will resume, okay. I am doing it a little fast. Okay, now after drawing this diagram, here we come at the place d dash. So there is no more values remain to draw or say draw lines, okay. So here it will be closed polygon to be balanced, okay. So O dash and D dash will be meet and will find something. So O dash D dash is equal to 7.1 centimeters. So it would be the value that would be equal to 0.04 my is equal to 7.1. After solving this we will obtain something. We will obtain what? What is the value? Let me calculate. Okay, it would be equal to 177.5 kg meter square. So 577 kg. Okay, sorry, 577 177.5 kg. So this is my. Here we could find the angle as well. Now theta y would be equal to uh, about, okay, 13 degrees, 14 degrees. Okay, theta y is equal to 14 degrees. And in the same way we could draw the force polygon, okay, by using the same table. So I'll draw just the rough diagram for this. Okay, so from O to A it is equal to 16. It is positive. Okay, so it would be like this. Now A to B it is 21 at angle 45 anti-clock. So A to B, say it is here over here, OA. Okay, sorry, OA. Okay, OA, it is B. Now BC is 24. BC is 24 at angle B to C is 70 degrees. Okay, anti-clock. So it would be over here, uh, 70 degrees, somewhere over here. Okay, now C to D it is about 120 degrees. It is 120 degree anti-clockwise. So C to D anti-clockwise. Okay, now D to E we have calculated that angle my. So from that we could draw this, and now at the end we have all the data completed, so we could join this and we will obtain this balanced force. Okay.